In an effort to dispel some of the mysteries of electronic music, we shall examine in the next hour the electronic music studio in the School of Music at the University of Iowa. Taking a leisurely and detailed tour through this facility, which is typical of such installations, containing a collection of electronic gear specially designed for the generation, the control, modification, and processing, and the recording of sounds. It should be noted that this equipment does not necessarily produce music. It produces instead an infinite variety of sounds. We may make the comparison with traditional musical instruments. A clarinet, for example, does not necessarily produce music, nor does a violin, nor a string quartet, nor an orchestra. It is rather people who make music: composers, conductors, performers. In the same way, it is the composer in the studio, not the machines, who produces music. Thus, our tour through the various technical apparatuses of the studio may be compared with a treatise on musical instruments, on orchestration, where we are exposed to certain basic sound characteristics of instrumental families and their members. In an electronic studio, however, we are dealing with sound characteristics at a more fundamental level. What is it that produces electronic sounds? Well, what is it that produces sound? Vibrations, of course, of a string, a reed, an air column, any struck object, which vibrates in certain ways and sets up waves of compression and rarefaction of air molecules, which we perceive when they strike our aural receptors, our eardrums. In the electronic medium, it is voltage that is vibrating, or rather oscillating, in certain ways, positive and negative, that is, above and below a neutral point of rest, and amplified, driving the cone of a loudspeaker, push, pull, in and out, setting up the same waves of molecular compression and rarefaction which we perceive as sound. An electronic synthesizer is nothing less than a collection of electronic modules which generate, control, modify, and process low-level voltages. With these things in mind, then, let us look more closely at a synthesizer. Let us look more closely at a synthesizer. The one before us consists of 4 carrying cases, each about 28 inches high and 20 inches wide, and each crammed with numerous modules, clearly labeled and differing from each other in their configuration of knobs and sockets. The knobs offer manual control of the module's operating characteristics. The sockets, or jacks, are various inputs and outputs designed to, as we say, patch one module to another by means of connecting plugs. Let us connect an output from this oscillator directly to the studio mixer, to which my microphone is also connected. Let us connect an output from this oscillator directly to the studio mixer, to which my microphone is also connected. We're listening to a sine wave, S-I-N-E, so called because its pattern follows the sine function, familiar to us from trigonometry. The oscillator also has outputs for 3 other waveforms: sawtooth, triangular, and pulse. This is what an oscillator does. Produces voltages, oscillating positive and negative, plus and minus, in a certain pattern or wave shape or waveform. As you can hear, each pattern, while it may be at the same frequency or pitch, and at the same amplitude or loudness has a different sound which we may define as timbre or tone color. As you can hear, each pattern, while it may be at the same frequency or pitch and at the same amplitude or loudness, has a different sound which we may define as timbre or tone color. The wave shape itself specifies the presence of overtones in a sound. Let's listen again. Note that both the sawtooth and pulse waves sound somehow brighter. It's because their sonic component consists of a fundamental and harmonic overtones. It is the presence and the dynamic pattern of these overtones which characterizes timbre or tone color, which enables us to distinguish between a violin, say, and a muted trumpet on the same pitch, or between the sound of one person's voice and another's, even on the telephone. We will return to this important characteristic of tone color a bit later. The oscillator, then, presents these four waveforms at a tunable frequency, whose range exceeds that of human hearing. As, for example, from the lowest, a sine wave, until it's really inaudible. Though listening to another waveform, such as a sawtooth wave, one can hear a series of pulsations or clicks, which are in fact the frequency of the waveform. The sine wave, going at the same frequency, has no irregularities in its structure, so really doesn't click like this. We don't perceive this waveform, though, as a frequency, as a pitch rather, until it's quite somewhat faster. Now I can jump to another range. And go right on out of human hearing. This low frequency, by the way, is not the lowest by any means. It's tuned to a pulse wave. Now, a pulse wave has 2 clicks per cycle. So that the frequency of this bop, da, 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 is about 1 per second. But we can slow this down considerably. And I haven't really even begun. The point of designing an oscillator that will go so low below the audio level is for purposes of control, and we'll discuss that in a moment. Let me return to another fundamental sound generated by the synthesizer. This is white noise, so called because as white light contains all colors, so white noise contains all pitches. These basic electronic sounds in themselves are rather uninteresting and uninspiring, no doubt. But isn't this true of the artist's paint squishing out of the tube, or a block of marble, or perhaps more technologically apt, the test pattern for color video broadcasting. It's necessary to go one step further with an electronic system to make these sounds somehow inherently promising. One direction is down the avenue of control, which I mentioned a moment ago. The frequency of an oscillator may be manually controlled, as we have heard, or it may be controlled by various other synthesizer modules. The most familiar of these, the keyboard, delivers a stepped voltage and may be played in the conventional fashion. The keyboard may, however, be tuned so as to produce intervals smaller than the half step, as in this quarter tone scale. The typical keyboard is thus really like a 50 or 60 position switch, applying preset voltages. It is not a polyphonic device, which is to say it only produces one voltage at a time. These voltages, by the way, unlike those from an oscillator, are DC or direct current. They are thus inaudible, since they don't oscillate, intended only for purposes of control. An oscillator may be used as a control device, and in this mode opens the door to myriad possibilities. When we control the frequency of one oscillator with another, we are modulating that frequency, or producing frequency modulation. When the control oscillator is below the range of hearing, or subaudio, we may clearly hear its waveform as it modifies the audible oscillator. The control oscillator is producing patterns of positive and negative voltage, so that, when positive, the frequency of the audio oscillator will operate above its tuned pitch. When negative, the audio oscillator will sound below its tuned pitch. For example, here is an audio sawtooth wave, whose frequency will now be controlled by a subaudio sine wave. And when we change the waveform of the controlling oscillator, we change the pattern of frequency modulation. Thus, obviously, the controlling wave is a sawtooth. And here it's a pulse wave. There are interesting possibilities in this sort of system, since the oscillators are so slow that they can be used in controlling rhythmic aspects of music. Now, just for fun, let's add more frequency modulation controls. I'll add now another pulse wave. And a sawtooth wave. And let's just hear what happens. I'll experiment with the frequencies of these controlling waves. I'll change the waveform of the audio signal, triangular wave. And its frequency. We're controlling a triangle wave with 3 subaudio waveforms. The subaudio oscillators are still going slow enough that they don't produce a tone, a pitch. But in combination, various patterns, pitch patterns are achieved. A lot of interesting possibilities in frequency modulation. This is, you've been listening to frequency modulation produced by subaudio control oscillators. When the control oscillators are audio, that's another matter entirely. And here, the sound output is rather unexpected. Let me get that triangle wave again. We'll control it with a sine wave, a fast sine wave. When you hear various tones, as I change the frequency of the control oscillator, hear various tones above and below the audio tone. These are called combination tones. We are discussing and illustrating characteristics of sound, and therefore, I would say, characteristics of an electronic music system. Combination tones, however they are produced, and in all cases they will be the resultant tones of two or more oscillations, are relatively simple arrangements of sum and difference tones, where the frequencies of oscillation are added together and or subtracted one from another. To illustrate, here's a variety of combination tones. These sounds dependent on the frequencies of the oscillators, on their waveforms, and on the amplitudes of the controlling waves. Although these sounds seem relatively complex, they may nevertheless be precisely calculated, as by computers, which may be programmed to produce the necessary voltages. Having produced a variety of tones, and we may also say timbres or tone colors with oscillators, let us approach this subject now from another point of view. Timbre is a manifestation of the shape of an oscillating wave, of its waveform. That waveform determines the presence or absence of upper frequencies or overtones, whether harmonic, as in acoustic or live sounds, or inharmonic, as in combination tones. There's an important family of electronic devices called filters, which may be used to modify a sound in various ways. The tone controls in your home audio system are of this family. Treble controls affecting the upper register of sounds, bass controls the lower. The filters in an electronic synthesizer offer much more drastic sound control. One type of filter, for example, specifies the frequency of a cutoff point above which any sounds will be severely attenuated. To illustrate, let us use the white noise generator. Here it is again, unmodified. The sound of your TV set on a channel that is not receiving a broadcast signal. Remember, white noise consists of all frequencies in a more or less continuous band throughout the range of human hearing. One type of filter, called a low-pass filter, will modify the white noise according to the variable frequency of the upper cutoff point. Another type of filter, called high pass, will modify any sound according to the variable frequency of a lower cutoff point. These filters may be used in combination. Upper and lower cutoff points specifying frequencies of the audible band. or, just the opposite, frequencies of a band which has been eliminated from the middle of a sound, so that we hear only what is above and below the cutoff points. Still another type of filter, called a filter bank, contains a series of band-pass filters whose center frequencies are fixed every half octave or third octave throughout the audio spectrum. As the frequency of each band is fixed, what is variable here is the amplitude of each band. Let us connect the white noise to a third octave filter and listen. White noise, as we have heard, is a rather raw sound in its unfiltered state. But when filtered, it can be exceedingly useful in music as it is in speech. For it is white noise we use to separate the vowel sounds in speech, our lips, tongue, teeth, and oral cavity shaping, filtering the noise. Our lips, tongue, teeth, and oral cavity shaping, filtering the noise. White noise, when filtered, is not only exceedingly useful in music. Surprisingly enough, it can be exceedingly beautiful also, as in the following example. I will improvise now a developing sound using white noise as the audio signal and modifying it with a fixed filter bank which consists of a series of bandpass filters whose center frequencies are fixed and through which the white noise will pass in a kind of screen. Let us listen to a piece of instrumental music through the screen of this fixed filter bank. also called a third octave filter. Now that's entirely too pleasant. Let us return to the low-pass filter again. This device offers two additional characteristics that I haven't mentioned. One is the capability of amplifying the cutoff point, making that very point above which the sound is severely attenuated audible. Since white noise contains every frequency, movement of this amplified cutoff point would result in a glissando. When our signal is one of the geometric waveforms, movement of the amplified cutoff point will make audible only those frequencies specified by the waveform, namely the fundamental and its harmonic overtones. When music students learn of the overtone series in school, the teacher usually plays the first few overtones on the piano as separate notes, whose intervals become smaller as they ascend. Thus, the fundamental, the octave above, a fifth above that, the second octave, a major third above that, the fifth again, then a slightly out of tune seventh, which of course we must imagine on the piano. Then the third octave, the major second above that, etc., in ever smaller intervals. And it is stated that all these frequencies are contained in the fundamental. A phenomenon we can accept, though we cannot experience it. Here, using a sawtooth wave as the signal, and the amplified cutoff point of a low-pass filter, we can experience the harmonic overtone series in all its pristine purity. The other feature of this filter I wanted to demonstrate is the fact that, like our oscillators, the filter may be controlled by external voltages, as the keyboard. A low-frequency subaudio sawtooth wave. Or several such low-frequency oscillators of different waveform. We've discussed and demonstrated oscillators and filters having to do with frequencies, or pitches, and with waveforms, or timbres. Another important characteristic of sound, in fact as important to sound as the domain of time, is amplitude, or loudness. And as you might suspect, a synthesizer has several devices for controlling amplitude with external voltages, as a keyboard. Or a low-frequency subaudio sawtooth wave. Now a triangular wave. This is amplitude modulation, which of course produces combination tones when the controlling oscillator is within the audio range. Another important device for the control of amplitude is an envelope generator, which produces, like the keyboard, a DC voltage of a certain pattern involving attack time, steady state, and decay time. The characteristic envelope of a sustained piano tone, for example, may be described as having a very short attack time, only a few microseconds in duration, when the vibration of the string goes from a state of rest or silence to its maximum amplitude, and a long decay time, several seconds in duration, with virtually no steady state in between. Back to the synthesizer now to demonstrate a few envelopes whose decay time is 0 and whose attack time is gradually increased. And now we gradually increase the decay time. Listen now to some effects produced by controlling a low-pass filter with the envelope generator. What happens is that the amplitude of the voltage pattern from the envelope generator regulates the frequency of the filter cutoff point, which thus regulates more or less of the overtones of the input signal, in this case a sawtooth wave. By controlling a filter with one envelope generator and an amplifier with another, and varying their DC voltage patterns, a variety of pseudo-instrumental sounds may be synthesized. Another device, called an envelope follower, produces DC voltages proportionate to the amplitudes of any audio input, so that, for example, amplitudes derived from my voice may be used to control an amplifier whose signal input is an orchestral work. Thus, an increase in the amplitude of my voice, as in certain stress patterns, will produce an increase in the amplitude of the music. This device is of great interest, as it derives voltages for use in the electronic music system from the real world. We have been discussing and illustrating a number of characteristic synthesizer operations, which turn out to be manipulations of basic properties of sound, as pitch or frequency, tone color, and amplitude. We have seen how these sound properties may be controlled by voltages operated manually or somewhat automatically, this operation taking place in the temporal domain. Control of time is naturally of great interest to the composer. One device which lends itself admirably to such control is called a sequential controller, or a sequencer. This instrument produces a series of 8 to 16 programmable voltages which repeat over and over at variable speeds until told to do otherwise. The sequencer is driven by an internal voltage-controlled oscillator. Therefore, its frequency can be controlled externally. The rate of the sequence cycle, or the durations of each stage, variable. Let us tune an 8-stage sequencer to produce a fairly simple voltage pattern, which will in turn control the frequencies of an oscillator. This simple voltage pattern then is controlling the frequencies of a sine tone. Each of the stages of the sequencer may be skipped, or you can stop at any one of them. Or certain durational patterns can be programmed. the rate of the sequence may be controlled externally, as with the keyboard again. Or with an external oscillator, say a sine wave. Or with a group of low-frequency oscillators. Furthermore, the voltages, as we have them tuned, may be multiplied. For example, multiply them by 2. Or by 4. The rate of the oscillator, of course, may be tuned faster. And if this is all this control is diminished, we're back to the original pattern. There just isn't time to go into all the manifestations of sequential control in electronic music. Suffice it to say that with artful use, sequencers offer a wealth of sonic material. But then this is true of the synthesizer as a whole. A composer working in some depth with a system may find himself organizing sounds of an orchestral density. The compositional problem, of course, is twofold. To create interesting sonic materials, which means knowledge and experience of characteristic synthesizer operations, and to organize them in a musical way, which means knowledge and experience of characteristic studio operation. For we have, in this hour, made a limited investigation of only half the studio. The other half is represented by the tape recorder and the world of tape and recording techniques. These matters we will discuss in a later talk. Thank you.